All right, so it's finally time now to construct the Lagrangian of NRQCD. So the way we're going to write this Lagrangian is we're going to divide it into three parts, which I'll call LU, LP, and LS. And the definition of these three parts is as follows. The LU part is purely ultrasoft, so only ultrasoft fields. The LS part has soft fields in it, so greater than or equal to 1 soft field. And any type of interaction that has a soft field, we stick in the LS. And then LP is everything else. OK, so that's going to be the way that we divide up the Lagrangian. So let's start with talking about LS. So when we think about LS, I said last time that these are radiative corrections to the potential. And I already drew some example diagrams, but let's draw them again. So this was example diagrams that, for example, could be some kind of vacuum polarization of the potential. I didn't draw the quark analog of that last time, but let me draw it this time. This could be a quark bubble. That's a vacuum polarization correction, just as well as the gluon interactions are vacuum polarization corrections. And we could also have other types of diagrams. In particular, these soft gluons, we could have a pair of them that come off of the fields like this, or like this. In this type of situation where the soft gluon hits the potential, this external guy had energy of order mv squared, and the soft one is bringing in mv. And that means that this guy here has to have mv as well, and so it becomes purple. It becomes off-shell with respect to the external particles. And the same thing happens in this diagram over here. OK, so there's something a little different happening in these diagrams than the ones over here. These propagators, once they become have energies of order mv, then they become propagators that are like HQET propagators. And so they become propagators that are like K0 plus or minus I0. And that happens both in this diagram for these propagators as well as in this diagram for these propagators. So this leads to a little bit of a complication. And the complication is related to the fact that when we know in this type of box diagram, if we have HQET propagators, that we get this so-called pinch singularity that we talked about. OK, so that's a little bit of a complication for constructing the soft Lagrangian. And there's two ways of solving that problem. And so I'll just tell you the two ways. One way is sort of to use the fact that we can really describe these interactions in HQET. So we do a construction that uses the fact that we understand HQET very well. So we use HQET. But then to avoid these pinch singularities, we use a property of the potential, which is called the non-abelian exponentiation theorem. And that theorem, which I don't want to explain today, is exactly allowing us to avoid diagrams with pinch singularities. OK, so that's one possibility. The other possibility, which is kind of more the approach that I want to advocate taking, would be to do a matching calculation to construct these interactions. And we would match order by order in V. And when we do this matching, we can actually assume that K0 is order mv, and we don't have to worry about these I0s. And so what we do is we construct Compton scattering type diagrams for the soft interaction, which I'll draw like this. And this then is containing in it the various types of interactions that we would have in the full theory, which include, for example, things like this, where this is Euler-Cross version, as well as the non-abelian interaction. And with this zigzag notation, I could also include in there the soft quark. So it's a sum of all these things. OK, and so that's a way of matching onto the soft potential, or the soft interaction Lagrangian. So we'd have a Lagrangian that would have our two potential fields here, the green, and then these two soft fields, which are the purple. And I'm not going to write down the Lagrangian for you, but I will tell you that this does give radiative corrections to the potential. And the type of radiative corrections it gives are things that would go like alpha s squared over q squared. So this would be a radiative correction to the Coulomb potential, 1 over q squared. And then you can get logarithms. The logarithms will be proportional to beta function because they're related to the running coupling. These are logarithms of q squared, so there's logarithmic potential. And then you could also have a constant. And if you were to calculate a soft diagram, such as the following one, this is exactly the result that this diagram would give. If I tied up 2 of these soft vertices, that's the type of potential that I would get out of that diagram. So that's what the soft Lagrangian does. In order to talk about the other Lagrangians here, I need to introduce a little bit of notation. In particular, we need something called the multipole expansion. So let me spend a few minutes talking about the multipole expansion. So the multipole expansion is just the way that we need to do the expansion here when we've got the 3 scales, the m, the mv, and the mv squared. And so if we think about our total momentum, it's been divided up into several pieces. We pulled out the rest mass of the particle. And then we are left behind a 3 momentum of order mv. But then there's also a smaller momentum of order mv squared. So we're dividing up here in terms of power counting that this is v to the 0. This one would be of order v. And this one would be of order v squared. And we're dividing up the momentum in that fashion. And we can do that in an analogous way to what we did in HQET. We can imagine that we've already pulled out the m, and now we want to pull out the p. And the way we can do that is by thinking about the p as being some kind of discrete variable and pulling out a phase associated to the p. And then the resulting field gets labeled by the p. And the residual coordinate x is then associated to this momentum k. So this is the type of multipole, momentum space multipole expansion that I want to use in order to describe NRQCD. And the point of doing this and switching to this field here is that this field has some very nice properties. In particular, the derivative on this field scales like mv squared, because the coordinate dependence is just carrying the residual k momentum. And so that means that we can now make a Taylor series expansion, for example, where I partial mu is much smaller than p vector. And that's how we're going to implement the multipole expansion. All right, so let's adopt that notation and now talk a little bit about this, what kind of interactions are in this LP. One of the types of interactions that's in the LP is just the potential itself. So let's talk about LP. And the potential in this notation here would have a sum over momenta, some coefficient, which is the potential. And then it'll have fields with these labels. So we have psi p dagger, psi p prime dagger, chi dagger minus p prime, and then psi p, and chi minus p. So the fields are in this label space. And then we have coefficients, which are the actual potential. So if we think about what this v hat is, it would contain, for example, the Coulomb interactions. So this would be a piece that's proportional to the TT bar matrices, some coefficient, which I'll now put a t to denote the color channel, and then p minus p prime squared in the denominator. And then there's subleading terms in v in this expansion. And I'll just write down one of them to give you an idea, where we could have something subleading where the p minus p prime squared is replaced by an m squared. Okay, and that would give you a subleading term. And there's 2 ways of getting the color structure. You could also have something called 1 tensor 1 instead of t tensor t, 2 ways of tying up the quarks and antiquarks. And this would give you a similar thing where a potential, you could also have a potential with a different color structure. So that's the way I want to think about the LP interactions of the quarks with a potential type of operator, where we're describing it by these 4 quark operators with a coefficient. And this is what I denoted previously by having just a colored dot. And now this colored dot could be labeled by any term in the potential. And in particular, the things that in the potential are these coefficients. These are like Wilson coefficients that I would determine by matching here. So let me just make a note of that. These are Wilson coefficients. OK, so that's the LP interactions. The next thing that we need to talk about are of course, the ultrasoft fields. OK, so the final thing that I want to talk about is the ultrasoft gluons. So let's turn to them. And so these are a type of interaction where, for example, I could have my potential fermion, and then I would have some kind of interaction with a particle, which is ultrasoft, like that. OK, so this would be kind of like a normal QCD type interaction. And if we think about what's going on with this type of interaction, and we think about the momenta, we can denote the mv and the mv squared piece by a combination of a bracket like this. And what the ultrasoft gluon brings in is it brings in some ultrasoft momentum, but it's only changing the part that's of order mv squared. So this final state guy would still have p here, but then it would have k ultrasoft in the mv squared component. And another thing that's important about ultrasoft gluons is that when we think about the propagator here, if we now think about the propagator for this guy, we might naively just say, well, OK, we've got momenta p and k, and we've got an energy p0. So maybe we should write p0 plus k0 minus p vector plus k vector squared over 2m. And that actually is not the right thing to do, because in this case, we've kept something small and something big at the same time. So really, in order to get the right propagator, we shouldn't keep that, and we should actually remove this k vector here. And then we have p0 and k0, which are the same size, and this p squared over 2m, which is the same size. And that's the right propagator to use when we're talking about interactions with the ultrasoft. So this is a multipole expansion. And we'll see how that's implemented in our Lagrangian momentarily. So let's write down a Lagrangian that does exactly that. So these are, again, part of LP. But now it's the part of LP that I'll associate with the kinetic term in the LP. And so I'm going to write this as a term that gives the propagator of the psi. So it's a psi p field. And then there's a covariant derivative. This is now a covariant derivative with respect to the ultrasoft. And now I'm splitting up the ultrasoft p, the ultrasoft d from the soft p in this term here. And then there could be other terms as well. So there's a psi p. So this is the type of Lagrangian we have. And this p has scaling of order mv. And this d has scaling of order v squared. So those two terms are of different size. So therefore, it's natural to split this up and write it as a sum over p, psi p dagger, I d0, minus p squared over 2m. And then this term will give a p dot id over m, where the 2 cancels. And then we'll have an id squared over 2m, et cetera. And then the power counting of these now terms can be done separately. These guys here are both of order v squared. This guy here is v cubed. And this guy here is v4, et cetera. And so if we write things out like that, then we can have a well-defined power counting for each of the terms. And the terms that give the propagator are just this ID0 and the p squared over 2m, which is why we just got the energy components, which whatever they were, and the p squared over 2m up here. OK, so that's how the Lagrangian works. And let me just note that the ID mu here is the partial derivative as well as the ultrasoft gauge field. OK, so what about the ultrasoft Lagrangian itself? Well, in some sense, that's the easiest thing of all, the ultrasoft Lagrangian. So the ultrasoft Lagrangian LU, which is sort of the final thing that we haven't yet talked about, is just, remember, purely ultrasoft. And if we just have some set of particles that have homogeneous scaling and they're fermions and gluons, that's just the QCD Lagrangian. So at lowest order in the interactions, when we think about what the Lagrangian is for the phi u, which is the ultrasoft quark, and the AU, which is the ultrasoft gluon, it's just the QCD Lagrangian for those fields. Okay, so that's the different pieces. We've talked about the LU, which is simple. The LS was what we started with, and there was these different pieces contributing in the LP, the potential, as well as these interactions between the potential fields and the ultrasoft gluons. And that gives you the full Lagrangian for the NRQCD field theory.